You see how the fundamentals can trip you up. Like imagine doing a math question and not knowing what this is. You can always take the log with that exponent as a base. Does everybody understand that part? That right there is the different aha moment. So now that I know that if this is the first term and this is the second term and this is the third term, I can utilize that to my advantage. All right, so chapter 1 is all about fundamentals for success in mathematics HL. First of all, understand that just because it's chapter 1 does not mean it's easy. Don't fall for that trap. A few things that you need to know about fundamentals is fundamentals does not mean that you simply learn it once and then you ignore it. All right, this is the mistake most students make. They go to module number 1, they go to training session number 1, they go through chapter number 1 of the mathematics, they learn it quickly, and then they move on with their life and then they forget everything that they learned. Bad idea. That is a very bad idea. Now, this is John Wooden. He is the coach. He's a legendary basketball coach. Long story short, right? When the season first started and all the basketball players were coming back after winning the championship, John Wooden made them do something very peculiar, all right? For the first hour and a half of their very first training on the very first day of the entire season, he made all of the star players, again, they just won the cup. He made all the star players do the following. He made them take off their shoes and then put them back on. Then he made them take off their socks. You put the socks on, you wrap it around like this, then you put it up, then you tie your shoes. And then once the shoes were tied, they were untied. They took the shoes back off. They took the socks back off and then they put it back on. And they did that for an hour and a half of the first session after being champions. Now, I think he did that for one big reason. It was to show that regardless of your skill level, regardless of where you think you're at, regardless of the success you've achieved in the past, if you don't master the fundamentals, they will take you down. They will destroy you. Your lack of knowledge with the fundamentals. And one of the fundamental skills of basketball is just having good feet, having good footwork. If your shoes are sloppy, if you lose traction on your feet, it doesn't matter how much skill you have, you're going to be incapable of fully utilizing that potential. So, long story short, you got all these basketball players, made them do the most monotonous, basic, fundamental task to showcase how essential it is. So here's the mindset shift I want you to have with regards to fundamentals. All right? Fundamental simply means high frequency. All right? I want you to forget for whatever reason in society we have this connotation that just because it's fundamental, it's easy, it's basic, it's not necessary. That's completely wrong. Fundamental simply means high frequency. Okay, that's the direct translation. If something's fundamental, it means it's going to show up many times. And it's going to show up multiple times right now and for all future sessions. All right, when it comes to boxing, there's only 6 fundamental moves. Jab, cross, right hook, left hook, uppercut, and then rear uppercut. So there's only 6 fundamentals, which make up nearly 90 to 95% of all the combinations you can make. Understand that you can draw a very similar analogy to mathematics, whereby if you understand the fundamentals, all the other math builds upon those premises, right? Also known as axioms. So let's first talk about the SL curriculum before we move on to the HL. All right, I think what I'm going to do in this session is I'm only going to cover the SL. And then in the future, I'm going to cover the HL. So when it comes to the SL curriculum, this is the stuff that we covered. All right. Number 1, we started with some basic scientific notation. Number 2, we talked about series and sequences. This is basically just formula manipulation. Typically, these are just add-ons for calculus and probability questions. Just down to understanding and utilizing these formulas. We start off with arithmetic, sequences, and series. The next is geometric sequences. The difference between arithmetic and geometric is that in arithmetic, you're adding by a certain value. So for example, 1, 2, 3, 4, 5, 6, you're adding 1 for every single value. For the geometric sequences and series, you're basically multiplying by the same value. So this would be 2, 4, 8, 16, and so on. So you're multiplying by 2 every single time. So compound interest, this stuff is kind of a joke. It's kind of a joke until you see this, what appears to be a scary looking formula. It's not. It's really not that bad. First of all, we talk about scientific notation. So operations with a number in the form of a to the power of 10 over k. All right. This is pretty straightforward. Essentially, it's the following. All right, you have a coefficient in front of the exponential. The way this works is that the number in front, so 2.5, gets multiplied by 10 5 times. And the way that exponents work in this case is that you're basically multiplying by 10 5 times. All right, so 5 is telling me how many times do I multiply that base number, which in this case is 10. How many times do I multiply 10? In this case, it's 5 times. And then I multiply that 5 times of 10 times 2.5. The purpose of scientific notation is that it becomes very easy, very simple to explain large numbers. Yeah, what's going on? So again, in summary, and I'm going to draw this out so that we all understand exactly what's going on, because again, we talk about tying and untying your shoe. If we have 2.5 times 10 to the power 5. Fundamental simply means this times this times this times this times this. 10 times. All right, untie your shoe, tie it back on. So 5 times right here, which essentially means that this can be written as 2.5 times 10 times 10 times 10 times 10 times 10 times 10. Now, what's excellent about scientific notation is that when you multiply tens together, you basically just count the number of zeros. So in this case, there's 5 zeros, 2, 3, 2, 3, 4, 5. Am I missing a zero here? Can someone correct me? What do you guys think? Am I missing a zero? Have I gone over a zero, or what exactly is going on here?
I think you're fine.
You see how the fundamentals can trip you up. In fact, I was staring and I'm like, did I add an extra zero? Because I thought that, the bug on my head, I thought that 100K was 10 to the 6. So my intuition was kind of leading me astray here. Turns out I was wrong. 10 to the 6 is actually a million, and a million is 6 zeros like this. So I think I might have gotten someone there. Long story short, this is why it's so important to just review these fundamentals. Like, this is basically what, when you go to college and you take some courses in real analysis or some type of advanced algebra, all right, what's the difference between algebra 2, which is the stuff you do in high school, and real algebra? All right, the difference between those two is that real algebra focuses solely on the basics. They focus solely on defining an operation such as addition. All right, what is addition? How do you define that rigorously? How do you prove it? It's a much more difficult question than people might think. All right, so long story short, this is scientific notation. The biggest thing about it that makes it so easy is that we know exactly how many digits there's going to be. So in this case, there's going to be 5 zeros. So you see here, we have 5 zeros here on our board. We have 5 zeros, 1, 2, 3, 4, 5. 5 zeros, this times 2. So it's just going to be this times 2 zeros. So it's just going to be like this. Cool. Next question, series and sums. All right, this is pretty straightforward. Basically just 95% is just formula manipulation. All right, so just look at the data booklet and understand how to manipulate the formula. If you do that, you'll be fine. I don't think there really isn't much else to say other than formula manipulation. However, you need to understand that series and sums, series and sequences, sums, geometric sequences, all this type of stuff, typically the way it's presented in the IB is that it's an add-on for polynomial, calculus, or probability questions. So at the end of a calculus question, they might add that the roots of this polynomial is a geometric sequence sum. All right, so then you just use the data from above of the roots of polynomial, and then you just add those up together. If you don't know what roots of polynomial is, don't worry about it. What you need to know for now is that this type of question, especially at an HL level, it's almost never asked by itself. Okay, they never just ask you to like plug things into a formula. Instead, there's some type of context, there's some type of more depth to it, and depth in the sense of it might come after a calculus question, after a polynomial, after some probability, after something. Okay, it's not just going to show up out of the blue. For SL, however, that is a little bit different. So just keep that one in mind. Here are the formulas that you need to know. All right, so just cram this down your throat. Understand how to do it. This really just comes from identifying what formula you need to use in what situation. So if it's an arithmetic sequence, use the arithmetic. If it's geometric, use the geometric. Okay, point blank period. There really isn't much else to say to this. If you are getting these questions incorrect, okay, remember we talked about this in the last module, but you need to identify what is your rate limiting factor. So in session number 1 of the Math Training Academy, the math version, and then in module number 1 of the Grizzly League Training Academy, we identified that there's always some limiting factor. There's always a rate limiting step that prevents you from achieving success. Whether that's in academics, whether that's with your goals, whether that's in you becoming your ideal best self, your best version of yourself, there's always some type of barrier that is stopping you from achieving that goal. Now, in mathematics, it's the exact same, right? And when I learned this changed my life. Because in mathematics, there's always something stopping you from achieving and getting the perfect score. Maybe it's you don't understand the formula, or maybe you lack a certain way to approach it. Or maybe you lack one of the ahas, right? You lack that intuition, that aha intuition that you need to figure it out. And you just need to do enough questions to build that aha intuition so that when you see a question, you instinctively know what to approach it with. But the point is, in every single question that you do, whether it's math, physics, anything, if you don't find the right answer, it's because there is some type of limiting factor, some type of roadblock that is stopping you from getting that answer. Whenever you study, your one goal should be to identify what that roadblock is. That should be your one goal, to identify what that is. And then, right, if you spend all of your time studying, attacking that one roadblock, that's how you win math. This is how you break math. Now, in the module number 1, I talked a lot about aha moments. This is typically the roadblock for most grade, like I'd say 5 to 6 level math IB HL kids. Okay, they're at the 5 to 6 level. They want to make it to the level 7, but the reason why they're unable to make it is because in order to make it to level 7, you need to develop an intuition behind how to apply aha moments, how to see patterns in the data, and ultimately, if you ever have like an A and B part question, how to utilize the first part and implement it into the second. That is typically the rate limiting step for most students. However, if you are not of that category and you're maybe getting like a 4 or 3 or something like that, it's probably something else. If you're not getting these questions if you're not getting these questions right here on geometric sequences and series, the rate limiting step in that is probably that you just don't know how to utilize these formulas. That's probably it. I would argue that if you know how to utilize these formulas, this will solve like 90% of the problems you have, like 95. The other like 5% just comes from understanding the context of the question and not screwing up. That's it. So the reason why I went through that mini rant about identifying exactly what the rate limiting step is because this is how you break not only Math HL, but any academic subject that you're doing. You need to identify what is the reason why, the singular reason why you're not able to get a level 7. And then once you realize what that is, you attack it and you spend no other time except doing that one thing. This is why I strongly dislike doing useless arithmetic when you're already good at arithmetic, because that's a distraction. It is a low value task. All right. And most people think it's fun, right? Yeah. It's fun to spend time doing arithmetic. No, like most students that I know don't want to spend all their time doing math, right? So instead of doing what's easy, i.e. arithmetic, simply because it's easy to do, instead do what's hard, do what's difficult, and then bank that time and do something that's actually fun, right? Like maybe go hang out with your friends, hang out with your family, read a book, whatever the case may be, not doing math if that's something you don't like to do. All right, so the point is, identify what that rate limiting step is and move forward. If we look at this question right here, or this part of the syllabus, excuse me, essentially what this speaks about is just the arithmetic, sequences, and sums. So this is from the actual syllabus itself. So the first formula, it's pretty intuitive. Essentially what this explains is that you have the nth term and then the first term, and then the nth term is simply the first term plus n minus 1 of the common difference. All right, so let me explain this a little bit better. All right, so let's say I have a arithmetic sequence as following. All right, I'm going to open this up. So I have 5, 10, 15, 20. All right, so this right here is term A4. This right here is term A1. So let's say n, in this case, is equal to 4. This is right here. So without using the formula, let's just figure this out. So we have A, without formula, it's just A4 is equal to A1, which is the first term, plus 5, plus 5, plus 5. All right, which is A1 plus 3 times 5. All right, now hopefully you see where the n minus 1 comes from. The n minus 1 in this formula right here comes from you understanding that for the first term, we don't add a common difference. And then for every term after that, we need to add the common difference. So it's just, more than anything, it's just an indexing thing, right? We start not on the n equals 0 term, but we start on the n equal 1 term. So the next formula we have to investigate is the sum of n terms of an arithmetic sequence. All right, so if we go back here to our arithmetic sequence, which is this right here, let's clean part of this up. If we go back here to our arithmetic sequence on the left-hand side of the screen, essentially, if we want to find, all these separate, the sum of all these terms up to, let's say, n is equal to 4, we simply use this formula. All right, which is, if you look closely, that is s is equal to n over 2 minus s is equal to u1 plus u of n. All right, so where on planet Earth does this come from? Well, I'm glad you asked. You can think of it from this way, all right? It's actually pretty intuitive once you realize what's happening. Essentially, let's say you were to try to add up all the different terms. All right, so you have, on the top, you have the exact same series and sequence, and the exact same series and sequence on the bottom. So you're adding the same thing twice, pretty straightforward. Now, what I want you to think about with regards to this is imagine I'm adding the sum. So the sum is this small amount plus this bigger amount plus this larger plus this larger. In other words, the sum is going to be, it's going to have like this type of shape, right? You just have the values bring it up. Now, let's say I do the exact same thing, but in reverse order, where I start with the largest one here, then the second largest, all the way until the smallest. The sum would look something like this. Now, this is what's beautiful about geometry, is that if you get this sum right here, and then you get this sum right here, and you add them up, right? Like you're trying to add two triangles to make a square. Essentially what you're left with is the first sum, and then this is the second sum, which gives me this square right here. Now it turns out that this square is made of sum n and sum 2. Therefore, I can divide this thing right here by 2, and that equals sum of n. So let me go through that one more time. Essentially, you have sum number 1 here, which is the yellow. Let's draw this out a little bit more. And then you have the sum number 2, which is green, just like this, which is taken from here. And then you have the yellow that's taken from here. There we go. You add it up, and then you get equal to sum of n when you divide by 2. So the entire, you're like, damn, yeah, like duh, like obviously. But hear me out. The reason why this is super important and the reason why this is critical is because if you look at this slide right here, notice how this right here is simply a. Right? In fact, I'm going to use a different color. So this right here is a1, and then this right here is an. So if I add a1 plus an, I get one length of this rectangle right here. So in other words, a1 plus an, this right here is equal to the length of the rectangle. Or excuse me, width. Width. So this is the width of the rectangle, right? And then if we look at the actual length, we have n terms, right? And this is the width, which we talked about was a1 plus an. So width times height. If this is the width times length. I'm so sorry about the confusion with width and length. Width times length is this. Turns out that if I multiply the width times the length, I get the size of the triangle, or the size of the rectangle. So sorry about the geometry. Size of the rectangle, which is exactly what you see right here. Then I want to divide this number by 2 because that gives me s of n. Right, this right here is equal to s of n now if I divide by 2. So I want to get this number and I want to divide it by 2. And that right there, ladies and gentlemen, is your formula. All right, next we talk about geometric sequences and series. It's just this part of the formula booklet. It's very straightforward, like just insanely straightforward. You need to understand that the difference between arithmetic and geometric is that geometric, you're just multiplying every single term by some other term. That's the difference. In arithmetic, you're adding it by a common difference, d. In geometric, you're simply multiplying by a term called r. All right, and then I can go through the exact same intuition behind this formula, but I'm not going to. Long story short, turns out that you can do something very similar, or you can prove it with induction, which is what we're going to do a little bit later. All right, so take a second and figure out this question right here. So I'll just say I don't know what the answer is. I did this question once a while back. All right, so I don't actually know. So this is basically the first time I'm seeing this for all intents and purposes. I'm going to show you what I think. I'm going to show you how I'm going to approach this. If I get it wrong, we'll figure it out together. All right, and I'll point out my mistakes and my reasoning, and we'll go through this together. All right, I'm not going to say anything. We'll see how this goes. Okay, so let's begin with the question. We're told that the first, so U1, fourth, and eighth term of an arithmetic sequence, the common difference being d, where d is not equal to 0, are the first 3 terms of the geometric sequence. All right, so let's do the following. U is the arithmetic sequence. And then, so I'm going to do arithmetic. This is going to be U. So U1, we're also told that the first, the fourth, and the eighth. All right, already I see some type of, I don't know if you can notice the pattern, 1, 4, 8. Something to notice. The other one is the geometric sequence right here. So I'm going to use A for this one. So we're told that the first term is the same as the first 3 terms of geometric sequence. So we're told that U1 is equal to A1. We're also told that U4 is equal to A2. We're also told that U8 is equal to A3. Does this make sense? Do we have any objections with this? Any questions? Maybe I'm doing something wrong. What do you guys think? Good? Yes? Excellent. So if that's the case, then we'll continue forward. That's the common difference of D, the first three terms of a geometric sequence with common ratio R. All right, so given that the first term of both sequences is 9. All right, so we're told that this right here is equal to 9 because this is the first term of arithmetic and the first term of the geometric. They're both the same and they're both equal to 9. Excellent. Now, so this is my thought process. Before I even start, I haven't even seen part A. What I've done to begin with is I've outlined all the information that I know. Okay, this is all the information I know. I know what U1 is. I knew what A is. I know that it's all equal to 9 just because there. I am making it very clear what it is that I know. Okay, we talk about clarity and just degrees of lead in general. Clarity is so fundamental for so many different aspects, especially in this case. If you know exactly what's going forward, you can utilize that to clearly understand how to solve the problem. So let's go back here. Given that the first term of both sequences is 9, find the value of D. Interesting. All right, so a few things to note. Okay, so this is my first reaction. All right, tell me what you guys think about this. And this comes back to, this is linear algebra. So something I learned in linear algebra here at university. Long story short, we have 4 different variables. We have U4, A2, A3, U8. All right, so we have 4 different variables. We have 2 equations. We need to somehow simplify. So when I see 4 variables and 2 equations, the first thing that clicks into my mind, okay, this is like the aha, this is the intuition, this is the stumbling block that some of you may have. The first thing that clicks into my mind is how can I simplify this further? How can I remove one of these 4 terms? Remove 2 of these terms? Remove 3 of these terms? How can I simplify it further into something that I know? Now, if you look at the formula booklet, right? Actually, before I reveal that, can someone tell me how I can simplify one of these terms? Let's say U4. All right, how can I simplify U4 down into something that I know? Yes, Gonzalo.
4 times U1.
4 times.
I don't know. No, I am a bit lost because I haven't been really paying attention to the first part of the class.
Okay.
So.
That was a good guess, though. You were very much on the right track, right? Apparently, the difference between arithmetic and geometric sequences is that arithmetic, you add a difference. So it would be something like 5, 10, 15, 20. Notice how there is 5 here, and there's 5 here. So there's a common difference called D. And then for geometric, it would be something like 3, 9, 27, 81. So notice how I'm multiplying by 3. Are we clear on that point? Excellent. So if we go back here, how can I rewrite U4 into something that I know, utilizing one of the equations in the formula booklet?
U4 is the arithmetic or geometric one, like the letter U?
Yes, arithmetic here.
Arithmetic, would it be 9 plus 4 minus 1 D? Right. That's the way you could rewrite it.
Good. So let's write the equation. So it's basically just U1 plus n minus 1 times D, right? In this case, n is equal to 4. So I can simply replace, we know what U1 is here, so it's 9. We also know that n is 4 minus 1, that's 3. We don't know what D is. In fact, that's what we're trying to find. We're trying to find the value of D. Excellent, that's progress. So we know that U4 can be explained in this way. Let's do the exact same for the other 4 terms. All right, so I'm gonna go through this a little bit faster. So U8 is just this, except it's 9 plus 7D. A2, if you go to the formula booklet back here, all right, there it is. If you look at the formula booklet right here, you can see that we have the nth term of a geometric sequence on the 3rd line, which essentially means that when n is equal to 2, I have A1, which is 9, so A1 times R, n minus 1. So in this case, A9 is 1 multiplied by R, which I don't know, to the power of n minus 1, which in this case is 2 minus 1, which is just 9R. All right, and then I can do the exact same thing with A3 minus 1, which is just 9 times R squared. All right, this is my initial reaction to this question. All right, what are your guys' thoughts on this? Do you think this is going to work? Do you think this is the best idea? Is there another solution that you guys may have? No? No one has anything else to say? I'm just trying to think of how to simplify this further. My intuition is telling me that this is not the right way to do this. Simply because if I try to do 9r and then 9r squared, I feel like we're going to get an annoying term. Like something, I think there's a better way. My intuition tells me that this might work, but there is a better way to do it. All right. So there is an aha moment here that I just realized. That's smart. Okay, so technically this is correct. This is one of the solutions. It is the uglier of the two. There's a very nice trick here. I actually really like the solution. There's a nice trick that I'm looking at the solution right here. Very nice trick. This is one of those aha moments and this is why you do so many questions. Once you see it, you can't unsee it. All right, I kind of feel bad for Harris if he doesn't end up seeing this because this is pretty cool. All right, check this out. So imagine I had this geometric. Okay, this is the high school way to explain it. I finally figured it out. All right, so you have this expression right here. Let's say you have these values. All right, so you have 3, 9, 8, 13. Let's say I also write this as the first term. So let's call first term A1. Let's call it U1 for the A1 for the geometric sequence. All right, so this is A1. This is A2 times 3. This is A1 times 3. This is A1 times 3 times 3. This is A1 times 3 times 3 times 3. All right, does everyone agree with what I just wrote on the board? Yes? Sorry, yeah, all right, cool. Yeah, just give me the claw, that way I can see you guys easier because I have like 4 displays going on here. So essentially, let's say I wanted to somehow equate these two. Turns out that I can get this term divided by this term, and this would be equal to this term divided by this term. Why is that the same? Well, look at this. We have A1 here, and we're dividing by A1 times 3, which is this term 9 right here. We're saying that this is equal to A1 times 3 over A1 times 3 times 3, which is that term here on the denominator. Well, it turns out that I can cancel these out, and I have A1 over A1 times 3, A1 over AY times 3, and these are the exact same. So, as a general formula, all right, so this is actually the much easier way to explain this. The general formula is the following, that A of K over A of K plus 1 is equal to A of N over A of N plus 1. So I can get every single number and divide it together. Why is that the case? It's because this is always equal to some number over some other number times the common ratio. Does that make sense? Yes. Yes or no? Jalal?
Where did you get the K from?
This is just some random number. I just said
okay.
some kth random term.
Okay. Yeah, no, everything makes sense.
Excellent.
Yeah.
So now if I know that this is the... So now that I know that if this is the first term and this is the second term and this is the third term, I can utilize that to my advantage. And I can do the following. That A of 1 over A of 2 is equal to A of 2 over A of 3. And now hopefully you see what to do next, right? Catherine, do you see what to do next?
Yeah, I kind of see it, I think.
Excellent. So basically what you do is you substitute this in if you want to find it. So you substitute U1 over U4 is equal to U4 over U8. That's it. And then you substitute it in and you solve for D. All right, Gonzalo, does that make sense? Yes? All right, and Jalal, you understand exactly what I'm talking about when I say this? Cool. So the entire point of this, again, let's try to learn some ahas. The aha moment of this is this identity right here. And I think the biggest takeaway, and this is something, again, I wasn't thinking about this, so it's an aha for myself as well. The biggest aha is that you can utilize these formulas. So we open this up. So you can utilize these formulas right here to get some pretty interesting properties. Notably that if I use the geometric sequence, of un is equal to u1 Rn minus 1, I can utilize this to cut away this R term if I was to divide it. Right? So let's say it's u, right? So let's say this is the next term. So it's n plus 1. It's the next one. These two terms end up cutting out. And then I'm just left with 1 over R. And the biggest thing about this, just like that. The biggest thing about this now is I can use another term somewhere completely random. Let's say it's k for some other random number. And I can basically do the same thing, assuming when I divide it out, I get R. That right there is a huge aha moment, at least for myself. All right. When I do that, this will also end up canceling out. All right, so how are we doing with this? Do you want me to explain parts? Please speak up. Please speak up. No? Okay, I'm gonna move on then. Cool, so this was a fun question. This right here should be a pretty routine question. I'm gonna leave it up to you. So when you watch the recording, pause right here and take some time and figure this out. It's not that hard. It's just looks like just some simple arithmetic plus the sum of the first n terms. I'd assume maybe some calcular work to find the number largest than 5,000. That's just my guess. I might be wrong though. So for the sake of time, do this one on your free time. It should be something similar. I have the feeling, because you have that U2, U3, and U6 are the first three terms of a geometric sequence. So you might have to use this ratio, a formula. Again, at the end of the day, this right here is all about formula manipulation. Just like myself. The roadblock I had there was I didn't see the aha in manipulating the formula. That's what I was missing. That's why I wasn't able to make it. All right, and here's another question. If you're watching the recording, take some time, go through this, and we'll go from there. All right. So the other big thing to note about section number 1. All right. So what I'm going to be doing, actually, I'm going to give you this right here. All right. This is supposed to be released on my YouTube channel in a, not do it there. This is supposed to be released on my YouTube channel in a few days, but I'll give it to you guys early. I think you'll find a lot of value in this video. You know what? I'll send that to you after this training. Okay, so what I'm going to do is I'm going to send you a video. Go until the end of the video. All right, and there are a few mistakes. It hasn't been edited. My editor is working on it right now. But what I want you to do is I want you to go until the end of the video. And at the end of the video, I talk about some induction strategies. I talk about some HL integrals, all that type of stuff. I think you're going to get a lot. So definitely check that out, especially given that we're all HLs. All right, so I'll give that to you as a bonus, specifically to Catherine, Jalal, and Gonzalo, who are here in this training right now. Cool. So let's see what else we got. So compound interest, this stuff is kind of a joke. It's kind of a joke until you see this, what appears to be a scary looking formula. It's not. It's really not that bad. All right, so essentially, don't memorize this formula. This is a bad idea. Most people who try to study this compound interest part, they try to memorize this formula. No, bad idea. Okay, I'm gonna put a huge X on this. Wrong. The reason why is because this is a hunk load of garbage. I was confused when I saw this formula. I didn't know what was going on. I saw all these different terms, all these different arrows. Don't do it. Instead, what I want you to do instead is to develop a strong enough intuition for you to truly know what's going on. All right, and let me explain to you what I mean by this. And I'm going to do so by writing this on the whiteboard on my left-hand side. So this is the formula on the right-hand side of your screen. Now, what exactly is interest? All right, well, let's say I have a number. Let's call it 3. Let's change this to black. Let's say I have a number 3. Interest simply tells me how much this 3 is going to grow. All right, so if it's growing at 10% interest, essentially what that means is that in the time in which it takes to grow, which let's say it's 10% per year, the 3 is going to be grown by 10%. And then whatever is left of that is going to be grown by 10%. In other words, if this 3 grows 10% per year, that essentially means that it's 3, and I'm going to be multiplying a 10% growth, which is 1.1. Does everybody understand why I put 1.1? Yes? All right. So we can do basic multiplication of percentages. Excellent. I kid you not, I see people and I'm like, it grows 10% per year. There's this, like, It happened to me. I remember one time a while ago, the kid did this. All right, that is not growth. Okay, that's like just use your intuition. If I get 3 and I multiply by 0.1, guess what? This is going to give me 0.3. Did that grow or did that shrink? All right, just sometimes we forget some basic intuition. Always ask yourself, does this answer make sense? So if I do 3.3 times this, I should get, what is this, 3.3? Does this answer make sense? If I have $3 and I expect it to grow by 10% per year, like intuitively, does it make sense that it's around that amount? 3.3, absolutely. Now, let's say I want to grow it another 10% in the next year. So I grow it 10% twice. Well, no need to fret. You simply get this, and then this is how much it's going to grow. And then since you want to grow what already grew by 10%, you're getting this number, and you're simply multiplying that, again, by 10%. All right. Does that make sense? Show me clause. Excellent. So if I want to do that again, one more time, let's do greener here. Pretty straightforward. Hopefully you guys are getting the gist. This entire thing now is 1 unit. Okay, this is 1 unit. And then you multiply this by 1.10%. So it grew by 10%, then it grew again by 10%, then it grew again by 10%. So at the end of the day, what you're really left with is if I want to grow it 10% for 3 times of interest, this is the exact same thing as 3 times 1.1 to the power of 3. All right, now look at this formula. If I was to tell you the exact same thing, like the 3% grows or 3 grows at 10%, would you be able to do it? Probably not. This looks confusing as, all right. So again, apologies about my language. I'm trying to be a little bit more composed. The point is, you look at this formula here on the right hand, on your left hand side. It's confusing. I don't know what to do. If you were to tell me like, all right, the $3 grows 10%, I look at this and I don't know what to do. Like I genuinely don't know what to do. All right, so no more of that. Hopefully that makes sense. Now, if we are to understand this formula a little bit better, this essentially 10% is just the annual rate, or also known as R. This right here is the time in years. All right, now let's say you have but yeah, you're completely correct. And by the way, that's some finance, the yearly annuity with the future value and the present value. That's finance 101 stuff. So congrats on knowing those terms. Long story short, if we look at, again, this equation just hurts my eyes, but if I look at it right now, and let's say I compound 10% every 6 months. All right, so I want you guys to do this question. I have $3 and it compounds 10% every 6 months for 12 months. All right. What is not the final number, because I don't want to crunch this into a calculator, and you shouldn't be doing that because that's just, again, a low value task of typing things into the calculator. I want you to write the equation that you would put into your calculator, excuse me. So take a second, write it down, and then we'll check in.
If I wrote it like this, would it work? So future value is equal to what the present value, which is 3. So future value is equal to 3 bracket 1 minus the increase rate, which is 10%, bracket to the exponent of 6. Would that work? And then just keep on increasing. Do you know what I mean?
Why did you use exponent of 6?
Because that's the period of time, of how it's compounding to get a bigger value.
You said per month? Is that what the annuity was?
Yeah. So per time frame.
Yeah, that could work, I guess. I'd have to look at the expression a little bit closely. From what you said, just from the top of my head, that seems like it would work. It seems more difficult though than necessary. All right, I think there's an easier way if you just think about this more conceptually. All right, so I'm gonna reveal the answer right now. Essentially what you're doing is you have $3 right here, and you then multiply it every 6 months. So, and you're doing that 24 months. So it's very straightforward. Like you can probably tell by this, but if I have 24 months and I do it 6 months, that means my 3 is going to get, I'm going to add interest to my 3 every 6 months for 24 months. So it means it's going to happen a total of 4 times. All right. So if it's a total of 4 times, essentially that means I have 3 times this 4 times. There you go. Agreed, disagreed? What do you guys think? Yeah? All right, cool. Like I'm just trying to look at this formula and see what the parallel is. Right? That's like I don't even understand this formula myself. And by the way, if I don't understand it, it probably means it's not going to be that useful in the actual IB exam because this was not asked, especially if you're in HL. I think just developing the intuition. Let me try to plug this in and see if I got the same answer. So I have 1 plus the annual rate. So yeah, so we're not even given the annual rate. We're just told that it's 10% every 6 months, which means that the annual rate would be, what would be the annual rate? I think it would be this squared. And then you multiply by 2 times. Whatever. I'm not going to confuse you. I don't think it's necessary. I think if you just use your intuition, you'll be fine. I've gotten all these questions correct in the past simply by just thinking through it. Damn, that text point is annoying. All right. Do I have any questions with this or are we good to go? Not that, with this. Excellent. Yeah, I kind of have beef with that formula after trying to explain it. So, sear this into your mind and we can go from there. All right. So just use your intuition. Exponentials. And this is what's laid out here with regards to the IB curriculum. But these are the rules that you just got to know. When we're multiplying 2 exponentials, you add up the exponent values. When you divide, you minus. When you do power, you multiply. And the rest of it. We also have this rule right here with logarithms. Change of base. So there's some log rules, which we'll talk about in just a second. But we talked about these last time, and I gave some berries to the students who completed it, which was Jalal, Catherine, and Gonzalo. Congrats. And these right here were the logarithms rule, log rules, essentially. So if you look on the top right-hand corner, you see that we have really just the base definition of a log, like this. All right, now how do you convert this into a log? Basically what you do is just remember that the base is always the base. The base of the exponent, the base of the log, it's always the same. So always the base. Okay, you see how it's the base of the exponential here? In this case, log of a of x. It is always the base right here as well. Always. So we talked about simplifying these logs. Boom, boom, boom. Take a minute if you're watching the replay and make sure you understand how to do these. Now, let's wrap up by doing a little more involved questions. So, first person to do this gets 150 berries starting now. So, go ahead. All 3 of these questions. Remember, speed and accuracy at the same time. I'll be here waiting. Give it a crack. Gonzalo, already done. Congrats. All right, so walk me through what was your answer for this one?
The first one's 2.
Yes.
The B is logarithm 6. Log 6 and 36.
Yes, that's correct. Let's quickly run through why this is 2.
Yeah, it's the same.
Yeah, so you can just go like this.
Yeah.
And then let me just real quick before you go on, and then you can use the log rule of addition. And then this is just 1, and this is just 1. Why is this 1? Well, think about what this means. What number x satisfies this equation right here? The answer is 1. That's basically what the log is. It's that value of x. Hint, that is also why 6 to the power of log 6 of 6. What does this simplify down to?
6.
Exactly. Turns out that if these 2 bases are the same, this entire thing just cancels out. And you just get 6. Excellent. And then you can just bring that down and think of it like that. So you said, which one for B?
It's it's also 2, the final answer.
Great. And you can just multiply it together, 4 times 9, and then you get the exact same thing as above. All right, and for number C?
Minus 1.
Exactly. And we can actually solve this. Nah, this is actually the easiest way to do it. There's another way you can kind of think about this, and then we can do the roll down the rim. Good. So with that being said, let's move on to the next question right here. There we go. So give this one a crack. And looks like we have an answer. Right, Gonzalo?
Okay, so for the first one, how do I explain it? I've used a formula. U2 equals to U1 plus 2 minus 1 plus D. I don't know if...
Yes, you can utilize the formula. That should work. You can also try to figure it out intuitively. So understand that this is an arithmetic sequence. I'm going to show you the formula way first. Turns out that, the value of U2 is U1 plus D times n minus 1, right? So, which is just U1 plus D. Correct? Catherine, are you following with this? Are you good? Welcome, Jalal. We can then utilize this. We know what U2 is. It's just PQ like this. This is equal to log of P plus D. Let's draw a better log. How about that? Agreed? Yes. Now we can rearrange for D. Log of PQ minus log of P. Now we know that there's a special term with this one right here where we can divide. So we get log of P over Q divided by P, which is simply log of Q. Agreed? Jalal, are you following? That's it. So that's for part B. For part A, excuse me. Now, Gonzalo, explain how you did part B.
With the other formula.
Exactly. Which is?
The summatory of 1 in this case equals to n times 2 U1 plus... No, I started using that formula, but then I changed to another one.
All right.
So I used the Sn is 20 equals to n divided by 2.
Yes.
And then U1 plus Un, everything in brackets. Yeah, that one.
Excellent. We know what Un is. Catherine, what is N? Are you sure it's 1? Exactly. So N is just the number of terms we have, which is 20. And then Gonzalo, what else are we missing here? How do we finish this off?
Yeah, you have to put the logarithm, but with, for example, in the U1 have logarithm of C and then P. So you can change the P by the C to the power of 2. And then that equals 2. And then you can do the same with the other logarithm, which is PQ. Change it to C to the power of 2 plus C to the power of 3, which can be both added to have C to the power of 5.
Okay. I see where you're coming from. Let's take a step back. I think you went a few steps forward.
Okay.
We want to somehow solve this equation right here. The question is, do we know what is in this equation? Well, we know what U1 is, right? U1 was log of P. We don't know what UN is. However, Jalal, what would UN be? How can we find that out?
I'm kind of lost. I don't really know where we're at.
All right, so we're working on question number B right here. Yeah, because you didn't have the time to look. So take your time. I won't ask you again. I won't cold call on you again for this question. So just take your time, look through it, make sure you understand. The question is, though, U of n, we can just simply use this formula. Right? That's why I'm saying that series of sequences is just formula manipulation. And it reaches a point where you just have to do enough practice questions for this to really sink in. And that's where you build the intuition. So we know that U of n is just U of 1 plus D times n minus 1. Cool. Therefore, if I want to find U of 20, which is exactly what I'm going to find here, that is simply U of 1 plus 19 times D. All right, everybody agree with that? Yes, let me just see the clause. Catherine? Excellent. So we have this as log of p. We also have now u of n. In this case, u of 20 is equal to, we can substitute this in right here, log of p plus 19 times d. What I'm going to do for the next math training, I think the way I'm going to hold this next time, is I'm just going to give you a bunch of questions to work on, and I want you to do them beforehand. And then when we come to the training, we're just going to go through the solutions quickly. That way, I think it'll be more productive that way, and we'll get the most out of it. Excellent. So we know that u of 1 is log of p right here. We also know that 19d, this is just log of q. Okay, why? Because d from part A is just log of q. Now let's make that substitution. We get that the sum of 20 over 2, because n is equal to 20, is log of p plus this thing right here, u of n, plus log of p plus 19 log of q. Everybody following so far? At this point, I'm essentially done. I just substitute things in. I don't think there's much utility in moving forward unless you want to practice some of the log rules. What do you guys think? Do you think it's useful to keep moving forward, or are we good from here? Like, would anyone not be able to solve the question? Would there be a limiting constraint? Would there be a roadblock that would stop someone from solving this question from this point? If there is, that's completely fine. I would spend more. I would go through it a little bit more. If not, we can move on to the next question. All right, so let's move on to the next question because I want to make the best use of our time that we have here. Let's do the following. So on my screen here on the left-hand side, I have a bunch of different equations to solve for x. Let's do the last one. All right, so start now. Okay, and we have an answer by Catherine. Do you want to walk me through your solution?
I'm not sure if it's fully correct. I might be wrong, but I used the long rule. So, well, first I moved the 11 to the other side, so it would be e4 minus 7x equals 9.
Okay.
And then long rule, so 9 equals e4 minus 7x would become 4 minus 7x equals log 9.
Okay. Cool.
And then I solved for x, so that was log 9 minus 4 over 7 over negative 7.
So 4, or you can just move this guy here over 7, like that. Cool, that is correct. Now, the aha moment here, and this is what stopped me for a long time, specifically myself when doing this, because I used to struggle with this type of problem, is understanding that I can multiply whatever on the left-hand side by the same on the right-hand side. Point is, me taking the lns of both sides can be done. This is okay. Why is this okay? Because it's the exact same operation. It's like adding 1 to both sides. Like, you can add plus 1 to both sides. It'll be the exact same operation. So when you have a ln like this, especially, or when you have an exponent, such as e or 2 or any number, you can always take the log with that exponent as a base. And you can do so on both sides to simplify the expression. That right there is the methodology. That's the aha moment, for myself at least. Now, once we have it like this, we can do the Tim Hortons roll down the rim rule. So we can utilize this right here. By the way, Tim Hortons, please sponsor me. Or like this, we get ln of e is equal to ln of 9. So why do we take the ln of both sides? It's because we can use the roll down the rim rule to then get an expression where we're multiplying by 1. So what you want to do is to take the log of both sides, and again, remember that log of e is simply ln, right? That's the only definition you got to know. I take the log of both sides with the base I want, and then because of the roll down the rim rule, I end up canceling and getting a 1. So that simplifies this complicated expression here on the left-hand side. It simplifies this down such that I can get an expression with only what's up here. Does that part right there make sense to everybody? If that makes sense, then you can do all of these questions. I have no doubt in my mind. It was once I learned this trick right here, or just this step. It's not even a trick. It's just a step in how to do it. That's when everything became clear. So let's pick the other question that I thought would be just as challenging. And it's this one right here. 7 of 1 minus x is equal to 4 of 3x plus 1. Think for a second. How would you solve this question? Let's look at this question right here. What was the first thing you tried to do, Gonzalo?
So I tried to have on both sides a logarithm so that I could operate with the several rules that we have.
Excellent. So you took the log of both sides, correct?
Yeah.
Just like this. Now what? By the way, but before you say something, this log can be any base, right?
Yeah.
This is just a short form way. Sometimes I write log instead of log. So keep that in mind. And the base doesn't matter. Whatever base this is, it doesn't matter. And frankly, it can be any base. The same way I can add any number to the right-hand side of an equation, right? The same way I can do this, like plus 2 or plus a million, minus 2 and minus a million, or excuse me, plus 2 and plus a million. So what I do on one side, I do on the other side is the exact same thing with log. The base does not matter. Keep that in mind. Yes, continue, Gonzalo.
So then I take the exponent and put it before the logarithm, both sides.
Good. So roll down the rim. All right, now what?
And now I multiply, for example, in the left side, 1 times logarithm of 7 minus x times logarithm of 7, and I do the same in the other part of the equation.
So you multiplied both sides by log of 7?
Yeah.
Okay.
With the rule.
What was your intention of doing that?
So that I could put the x's in one side and the other numbers in the other.
Okay. So you, just so I understand, you want to multiply both sides by log of 7? Like this?
No, not that. No.
Ah.
Like taking the parentheses and it's like
And expand
1
it.
times logarithm of 7 minus x times logarithm of 7.
Got it.
Yeah, that way. The same on the other side. 3x logarithm of 4 plus logarithm of 4.
Okay, now what?
Now I put the x in one side and the numbers in the other.
All right. And now?
And now I put I don't touch the left side, and in the right side I put x and then parentheses 3 times logarithm of 4 plus logarithm of 7.
Excellent. So in other words, you factor out the x.
Yeah.
Cool. So does everybody understand what Gonzalo did right here? Yes. Put up the grizzly claw. Questions? Questions, Jalal? Excuse me.
Pat, I was just curious on how he knew to do that. I don't know how to explain it. The step before the arrow.
This step right here.
Screen. Yeah.
Yeah, so that's the aha moment. This comes up again in the functions chapter. This right here, Jalal, I need you to memorize this type of just format. If I have this multiplication, this can be some random number, and I want to solve for x, this is almost always the way you do it. You factor it out, you then rearrange, and then you factor the x out, and then solve for x, okay? Let me give you a quick example of this in some other place. All right, let's say I want to take I have some function, y is equal to f of x. By the way, we all know what this is, correct? Now, if I want to take the inverse, turns out that x is just the inverse like this. You know what? I'm not going to explain this in depth because it's going to take too much time. But what I'm trying to say is that this is going to come up again when you do something like that. All right, so just remember, when you have an inverse like this methodology, this aha moment right here of first factoring it out, then rearranging, and then putting the x in front, and then solving for x, that's how you do it for logarithmic questions and also for this right here. Let's do another. So do this for homework or in your free time or whenever. And then this right here as well. Excellent. So with that being said, we talked about this with the example that I just gave, left-hand side and right-hand side. The way you prove this is not by, the way you do any proof is not simply by saying that 1 is equal to 1. Don't do that. So for example, if I have, you want to prove that For instance, you want to prove that 2 plus 1 is equal to 1 plus 2. What you don't want to do is say, all right, 2 plus 1 is 3, and this is equal to 3. That's invalid. Instead, you say, all right, the left-hand side is 2 plus 1. The right-hand side is 1 plus 2. Then I write that out. All right, this is 3, and then the left-hand side is equal to the right-hand side. That's the proof, okay? You want to make sure that the left-hand side is equal to the right-hand side, and that shows your proof. That's the best way to do it. All right, so this right here is another of the topic guidelines they need to understand, some of the content for the Math HL. Essentially just showcasing left-hand side and right-hand side proofs, which is what we just covered. The other part to this entire equation is summing infinite geometric sequences. Now, if this is not intuitive already, let me just briefly explain. How exactly does how does an infinite sum of stuff summarize to a finite amount? All right, how does an infinite sum to a finite amount? Well, it needs to do what we like to call converge. All right, so this right here is called converge. This is when the sum gets smaller until it reaches at point infinity, reaches basically 0. Now, this is the age-old question of if you had a bunny rabbit that had to get from point A to point B, just like this, and the bunny rabbit could take steps that would half the distance, would it eventually reach point B? Well, it turns out that the answer is yes. The bunny reaches B. Now, the reason why this happens has to do with the properties of infinity. Us mere mortals, we cannot conceptualize the content of infinity. At infinity, strange things happen. And it turns out that if you keep having, and you're consistently reaching there, at a state of infinity, meaning that you've gone an infinite amount of times, you're going to make it. Another way to think about this is as follows. Let's say I had a square, and I cut the square in half, and then I cut the square in half, then I cut the square in half, then I cut the square in half, keep cutting the square in half. Eventually, as I approach infinity, I would have covered the entire area. In other words, if I summed from I equaling 1 to infinity, what would this equal? Yes, Gonzalo.
Will it be 1?
You are correct. Excellent. Sum of an infinite geometric sequence. U1 over 1 minus R. There we go. So U1 is 1/2. 1 minus 1/2. 1/2 over 1/2, which is 1. So it turns out that the bunny rabbit does end up reaching the end point, and then we do end up narrowing down. So that was the talk on infinite geometric sequences. 9 times out of 10, you're just going to have to, in fact, 99 times out of 10 out of 100, you're going to have to just utilize this formula, and that should be good enough to go. So let's finish off the SL part of the topic number 1 by looking at the binomial theorem. Okay, this right here is the binomial theorem. Essentially what this means, it's actually very straightforward. If I have some type of polynomial like this, a plus b, let's say to the power of 100. Instead of doing the following, like going, all right, I'm going to do a times b like this, and then I'm going to like do the multiplication and then try to like, this is not a good use of my time. Hopefully you see why if there's 100 cases. Turns out that there's a very easy way to do this utilizing this formula, where you utilize the theorem here on the right. You can substitute in the values and just get a sum of different values. All right, so let's say I want to find this. Well, I can substitute 100, and I get this interesting looking expression. Starting at k is equal to 0 of 100, and then b to the power 0. And then I can do, plus n is always equal to 100, k of 1 times b of 1. And then it just keeps going until I reach the end, which goes upwards of a show of claws. Who has done this theorem before? Who understands what this is? I see Jalal. Catherine, have you done this before?
I've done
Yes.
something similar to this, but not using this type of formula. It's like a different one.
All right. Is it this one right here? Catherine, do you have experience with this? Have they taught this at your level yet?
Yes, it was like, I think it was the very beginning of last year, actually. But
All right.
yeah, I'm familiar with it.
Excellent. So this will be some review for you two. And Gonzalo? No? Never seen this before. All right. So that's interesting. Now I have the following. Okay. X minus 2 to the power of 4. I want you to utilize this formula to simplify and expand. So there's the formula on the right-hand side and the expression on the left. So take a minute and you can figure it out. All right, so try again using the formula. This should be pretty straightforward with the formula though. You just plug in the numbers on the right-hand side. So give it another shot. And when you're done, does anyone else have an answer? I see Gonzalo. Yes, Gonzalo.
It's not an answer, but I just put the numbers in the formula, but I don't know what to do afterwards.
Okay. So let's just do exactly that. So we know that n in this case is 4. So we have the summation to 4. We also have that k is equal to 0. And then we get that if n is equal to 4, we can just substitute this in. So we get 4 of k like this. Are we all clear on what this k means or no? You're a little confused, Gonzalo? All right, so this k right here essentially is I'm not sure what the technical mathematical term is. It can be thought of as the variable that we're iterating through. So we start off with k equaling 0, and then we iterate to the next, and in this case, k is equal to 1. Then the next, k is equal to 2, and then the next, k is equal to 3, then 4, then 5. So notice that when k is equal to 5, we're at the stopping condition up here. So we're done with the summation. So what we're doing right here is we're basically iterating from k equal to 0 all the way to 4. So of this expression, how many terms should we have? What do you guys think? How many terms? 5. Excellent. So we have exactly when k is equal to 0, when it's 1, when it's 2, when it's 3, when it's 4. So we have 1, 2, 3, 4, 5 terms. 5. There we go. Now if we add the next part, we see that, first of all, n is equal to 4. Now a is just the first term here in the expression. So a is equal to x. And then b is simply this term right here. Notice that b would be negative 2 because there should be a positive up front. By the way, this is very important. This is where a lot of mistakes happen. B is negative 2 plus this b, so brackets negative 2. So understand that b is negative 2. That's what we have. Plugging this in, just plug it in, right? And we get n, in this case is 4. So we get 4 minus k, and then let's just copy and paste what's in the formula and the expression right here. So we have that this term right here is b. This is b. Therefore, we can just replace b right here like that. And then we're just multiplying to the power of k. So what we're doing here is we're literally just plugging into a formula. I don't think you need to know much knowledge apart from that. Really what you're doing, there's a lot of knowledge and understanding where this formula comes from. I'm not going to spend time deriving that. In fact, you can prove this with induction. Long story short, a is x, b is negative 2. You plug that in, and then you're good to go moving forward. And you know that n is also 4. So if we expand this further, we can essentially just plug these numbers in and expand the summation. So let's say when k is equal to 0, which is the first term, so k is 0 for the first term, we get that 4 of 0 is equal to x to the power of 4, and then negative 2, 0, like this. Plus the next term, plus what would be the next term that we add down here?
Is it 4 and 2 for like the bracket?
Perfect. And then anything else? X to the power
X,
of
4 minus 2, and then brackets negative 2, 2.
Perfect. That's exactly it. And then we can just keep going this on and on. So notice how we're iterating through k equal to 0, and then we're going to k equals 1, and then we're going to k equals 2, all the way until, so this will be k is equal to 3, and then we finish when k is equal to 4. So there's 2 more terms, basically just the exact same thing down here. Does everybody understand this? Yes. Show me the claw so I can see. Excellent. So with that being said, let's go on to the next question, which is this one right here. We just did it. Now, let's say I want to find an individual term. This is the expression. And hopefully it makes sense if you look at the formula that we used. Because this is just one instance of the summation. If we look right here, this is just one instance of what we're summing up right here. So notice how the formula on the right-hand side is literally just this. Does that make sense? Do people understand what is going on here? This is just the kth term. So if I want to find the kth term right here, turns out that this right here is the term when k is equal to 0. This is the term when k is 1. So the t of 1th term is this right here. T of 2, 3, and 4. Are we following that? Yes? Catherine? If not, please let me know. Please stop, because I understand if you haven't learned this, if your teacher hasn't explained it properly. I'm going through it very fast. That way we can cover the rest of the content. If not, I'm going to move forward. Now, what you want to do is that we know this right here. We know that n. It's given. So, like, maybe we get a question where we want to find n, but 99% of the questions we know n. Look at this expression again. We know that x minus 2 to the power of 4. 4 is n. N equals 4. So we know what n is. Interesting observation. So we know what n is. That's given. Typically, our goal will be to find k. We don't know what k is. Now, what is k in this expression? Remember again that it's the term that we're summing in each iteration. So as we'll see in the next question, sometimes we know what t of 1 is or t of k is, but we don't know which term it is in the sequence. And that is actually very important. I'll explain that again in just a second. What I want you to take away from this, though, is that our goal typically is to find k. This is, again, 95% of cases. We want to know what k is. And then once we can find k and n, we can just simply plug that in and then find the term that we're looking for. And we can use that to get the coefficient. So what I'm going to do is the following. Look at this expression right here. Can someone tell me what part A is? Write down the number of terms in this expansion. Yes, Gonzalo.
A is x to the power of 2.
For the number of terms?
Number of terms.
Yes. So we're going to expand this out, right? We're going to expand this factorial. Excuse me, not the factorial. We're going to expand. We're going to factor it out. How many terms are we going to have?
10.
Very close.
11.
Exactly. Because remember, when we write out the formula, we're going to go from k is equal to 0 up until k is equal to 10. And this 10 right here is n. So we have 0, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 plus the 0, so plus the 0th term, which is a total of 11 terms. Now, I'm going to show you how to do part B, and then you're going to do this question right here, okay? So I'm going to show you how to do part B right now. What we want to do is we want to find the coefficient of 8 we want to find the coefficient of x to the power of 8. So let's start off by writing the general term. This is typically where you want to start. The general term is this formula right here, which we just talked about here on the right-hand side. It is simply a to the power of n minus k and then b to the power of k. Cool. I just wrote down the formula. Let's plug these numbers in. So n is equal to 10, We don't know what k is. We want to find what k is if we want to find the general curve term. And then a is simply x to the power of 2. This is a. And then we raise this to the power of n minus k. Since n is 10, we subtract 10 minus k. And then we multiply by term b, which is 2 over x to the power of k. Is everybody following this right here? Yes. Excellent.
I have a question.
Question. Go ahead.
Can you use Pascal's triangle to solve this instead of like using like this way? Would it work the same or is it like different?
You can use Pascal's triangle. That's another method.
Because that's the one I've been taught, like to do this stuff. That's why I'm sort of confused, like seeing this kind of format.
All right. I learned both methods. I can tell you right now, this one's much faster. This one's optimized for exams.
Okay.
Or I'm not saying the other one's wrong. The other one can work. I've just learned that this is much faster going it this way. All right. So I think it would benefit you to learn this. Also, this is much easier than the Pascal. Once you start to understand that you're literally just playing around with formula, it's just algebra. It's not trying to figure out Pascal or anything like that, which is combinatorics. And combinatorics are typically more difficult than algebra. So I plugged in 10. I plugged in all the values here. Now, I'm going to do some algebra and I'm going to simplify this further. For most people, this is a stumbling block. They're unable to simplify this expression further. So I'm going to do it before your eyes, and I want you to tell me if you have any questions. So what I'm going to do is I'm going to use an exponential rule right here to multiply the 2 and the 2 with the 10 minus k, like this. Then I'm going to expand this out further. So this is one term multiplied by x to the power of negative k times 2 to the k. Everybody agree with this? Excellent. This is just basic algebra. Now I'm going to simplify this even further, and I'm going to collect like terms. So x here is a like term, x here is a like term. Yes, let's look at exponential rules. So if it's the exact same base, we can just add them up. Agreed? All right, so let's do exactly that. Since x and x are the exact same base, we can just add these up. So we're just add these up. We have negative 2x minus x, 3x like this, and then 2 to the power of k just like that. All right, cool. Now this right here is the general term, t of k. So let's recap what we did. We expressed this term here on the left, on the right-hand side as the general term. We plugged in the values, a equal x squared, 2 over the x, and then we just simplified it further to this. Now, this is where the magic comes in. We want to find the coefficient of this term right here, x to the 8. This is the aha moment. Once you clearly understand how to do this, this question becomes so easy, so incredibly easy. So we want to find the coefficient of this term right here. Now, this term, so we're trying to find a, that's the coefficient. We want to find this value. Turns out that this term is equal to some term in the sequence. Some term in the expansion of this binomial is equivalent to this term right here. The biggest thing to understand is that since we're looking for the coefficient of x to the power of 8, we know that this is somewhere in the expansion that we originally want to find, right? In the term right here on the left-hand side, in the x squared plus 2 over x, all of that to the power of 10. So if I want to find the coefficient of 8, notice that now I have two unknowns. I have the coefficient itself, which I want to find. I also have k, which I told you, right? I warned you that we need to find k because we don't know which term in the sequence will give us x to the power of 8. We don't know which one it is. So we got to find this k term. Well, this is very simple because we know that we're looking for the case where 8 is equivalent to this power right here. In other words, we're looking for k where 8 is equivalent to 20 minus 3k, where this 8 is equal to this right here. Since this is a term in the expansion of the binomial theorem, in the expansion of the term, that must mean that there is an x to the value to the power of something that is equivalent to that value of 8. Does everybody understand what I just did right there? Understand why I add these up? Gonzalo, you confused?
What are you doing with the other part of the... Like, I understand why you want to have on one side x to the power of 8 and on the other side x to the power of 8, but the other things?
Yeah, so this is the coefficients, which we're going to find in just a second.
Okay. Now I can understand.
Okay. Yeah, so these two are coefficients. So these two are equivalent to each other because it's the same coefficient. The exponentials are also equal to each other because it's the same exponential. So now we should be able to find k. I'm going to 3 is equal to 12, and then k is equal to 4. Cool. Now I have k. And guess what? Now that I have k, I can simply plug k in here and find the coefficient. So that's exactly what I'm going to do. I'm going to copy and paste this right here. Oops. I'll copy this. Boom. Thank you, tablet. There we go. We know that this, when we substitute it in, we get this right here. Which is also equal to a, which is the coefficient. Okay? Now, the question becomes, what is this thing? Like, what is this 10 bracket thing? This is simply it's known as a choose operator, which is very complicated. But essentially, it tells us the number of ways that we can choose 4 things from a group of 10. So if we have 10 objects, how many times can we choose 4 of that 10? Let's think of an easier example. So let's say I have 3 marbles and I want to pick marbles in groups of 2. Okay, how many ways can I pick groups of 2 from the marble? Well, it turns out that there's a few different ways to do it. I have these 3 marbles. I can start off by making a kind of like blue. I can make a group here. I can then make a group here. I can then make a group here. So essentially what this tells me right here is that if I want to find how many groups of 2 I can take from 3 marbles, what would this number be? Three. Exactly, Gonzalo. That's all it says. Does that make sense, Gonzalo? Excellent. So, real quick, I have a bunch of marbles here. I want to pick how many groups of 2 I can choose from the group of 3. And it turns out that if I have 3 marbles and groups of 2, I want to pick how many groups of 2 I can pick of the 3. There's only 3 different combinations that I can choose that'll make this work. And then Jalal, back to your point, if you map out all the different values of n and of k, you get this, what's known as the Pascal triangle. All right, let's find what the coefficient is. Here you would just use your calculator. So you can plug this number in. Excuse me. If you go to math and then you go to probability, so you go math, then probability on your TI-84, and you select the third option, which is NC are 3. You can then do 10, choose 4. And then the answer you should get is 210. So there are 210 ways to choose 4 marbles if I had 10. Someone wants to say something?
Yeah, I was just going to tell you the answer.
Which was?
210.
Exactly.
Pascal's triangle. I did the Pascal's triangle.
Yeah, so that's the other way to do it. You can figure it out that way as well. And that right there, ladies and gentlemen, is your coefficient. 3,360. So the methodology to do this. Once you've done this a few times, what I want you to do after this is to just go to the question bank and shoot through as many questions as you possibly can. All right? Do as many as humanly possible. That's how you do this. Specifically on this expansion. And once you do it a few times, you start to get the hang of it. It becomes so easy, it becomes second nature. This is how you break IB. You just do this stuff a bunch of times. Now you know what the aha moment is. The aha moment is understanding this expression right here. Then you simply substitute in the values. You simplify it. You're then left with a simplified version of that. Now, what you're missing in order to solve this is which value of k satisfies this term. So if I was to find the coefficient when x is equal to 8, I want to solve for k so I find which k in the term works. Rearrange for k, find k, which is 4. Plug that back in here, get the coefficient, and then solve it. Does that make sense? Excellent. Catherine? Catherine, do you have any questions with that? Are you okay?
I'm open.
Excellent. All right, so with that being said, let's do the following. Find term x cubed in the expression. So essentially what you wanted to do was, this is very important, everybody. So you wanted to find, you know that this ends up, you know that somewhere in here, there's going to be a term that is x squared, and there's going to be a term that is x to the power 3, correct? So somewhere inside of this expansion, there's an x squared and an x cubed. Why is that? Well, remember what we're doing when we expand the binomial distribution. We're going to get x to the power 4, x to the power 3, all the way to x to the power 0. Right? Every single term will contain one of these values. The reason why this is the case, if you just look at the formula, we're going from k0 up to k4. And it's always going to be iterating through k. Does that make sense, by the way? This is just basic binomial theorem. You just expand something to the power 4. This is how many different x's you're going to get. Yes, no, yes, excellent. So then, Catherine, what did you do after that?
Well, after identifying that there's an x squared term within the second bracket.
Yes.
I used the formula and applied that to find the coefficient of the term. So that would be, should I just go into that, or is there other step I should explain before that?
So essentially what you're doing is you want to find the coefficient of this term.
Yes.
And the coefficient of this term, correct?
Yes. No, you don't have to find it for the x cubed, right? Do you? Oh, wait, no. Never mind. I forgot to do it for the x cubed. That's it. Yeah.
Mm-hmm. So yeah, so you want to find it for the x squared and for the x cubed. Why? Because you're multiplying by plus 4. In other words, and this is the most important part, everybody, this is what I'm trying to get at. This is the takeaway. Since you know you're going to end up multiplying it by this, these two terms are eventually going to multiply. So notice that eventually I'm going to get x cubed because it's x times x squared. And I'm also going to get x cubed right here because it's x cubed times some constant. Does everybody understand that part? That right there is the different aha moment compared to the other question that we talked about. Good, Jalal? Yes. Gonzalo?
Why a 2 and a 3?
because this is the only cases in this question right here where I'm going to get the x cubed term, right? We want this term right here. We know that when we expand this, which remember, it's just this part here on the left-hand side, this is the only case when we multiply x squared by x, is the only case we're going to get x cubed. And same can be said there. All right, cool. Makes sense? So what we're trying to do is, if we were to write this fresh, what we're really trying to find is step number 1, find the x squared and x cubed terms of that right there. Because when we do that, we can then multiply it by the fraction there on the left-hand side. By the expression on the left-hand side. And that'll give us the x cubed term. Agreed? Show me your claw if that part makes sense. That's the big aha moment. So now, excellent. It's the exact same thing as before. We just do the exact same thing to find the binomial. Literally what we did back here. It's the exact same thing. We expand it out, and then we go from there. All right. So we're right at 3 p.m. right now. I do not want to go on any further, or else it's going to be too much information. Information overload, as we talk about in Grizzly Elite Training Academy. Thank you so much for coming to this math training session. Please take some time. You should be able to figure out the rest of this problem. After this, it's just algebra and utilizing stuff we learned earlier. Okay, so there's no more tricks. There's no more aha moments. It's just crunch the numbers, multiply it out, and then get the final result. All right. Does anybody have any questions before I finish this one off? In fact, I'm going to stop the recording right now.